like lumps. Here's a lump solution to the Kp equation I just wrote down. It's rational in x and y. And there it is, moving along, and in x, it's got a little bit. We did some calculations because we have some methods that work very well on both Kp and Benny-Luke, and depending on the values of the small parameter, the solution of Benny-Luke and Kp analytic pretty much are very, very close. These are for typical values of the parameters in this moving coordinate system. And you can plot how the speed in x moves versus the maximum. You see that only when the speed is very large and mu, the small parameter, is fairly large, do you start getting deviations between Benny-Luke and Kp. Basically, Benny-Luke codes in a lot of what you expect from Kp. So, Benny-Luke and Kp both have lump solutions effectively in them. We also looked for lump solutions in the full reformulated one-wave equations, and we found them for small ranges of parameter. I will go back there once I have a student that I feel we can spend a lot of time on that problem. But right now, the best I can say about the full one-wave equations is for small ranges of the parameter, we get good agreement with Kp. But after that, the numerics aren't working so well. So where are we here? Small amplitudes, long waves from the full one-wave equations. Take just the first term, you find Benny-Luke and Kp. We also, and I'm not going to talk about that in this lecture, we can find NLS type equations. Why do they come out? Well, the business of deep water, you get groups of waves. What do you get groups of waves? You take an initial condition, it separates into groups. The groups move with rapid waves, with slow amplitude. They satisfy nonlinear Schrödinger equations. If you look for such a monochromatic wave expansion in those non-local equations, use the Riemann-Lebesgue lemma, you find the nonlinear Schrödinger equation. But I'm not going to go into the details here. What I am going to talk about are traveling wave solutions in 1 and 2D to very high order. Let's talk about 1D solitary waves to very high order. We can find, because this method is so easy, you just expand Koch, you just expand Sinh, take a Fourier transform, and out comes a series of equations to very high order. You can automate this. So Terry Howe worked on this, and he came up with a series, eta in terms of sesh to even powers. And we went to 14 orders. Probably what I present is 9 orders. 9 orders of sessions to even powers. The coefficients depend on surface tension. This was studied by Longin and Higgins and Fenton in the 70s for sigma 0, for no zero surface tension. When you put surface tension in, unfortunately, the calculations get very, very hairy. At any rate, you get a series, I present only the first 2 terms. 9 orders. In epsilon. Okay? And eta of 0, we normalize to be 1 if sigma is between 0 and a third, and minus 1 if sigma is greater than a third. That means the maximum occurs at the origin, and either it's a bright solid side, right? Either it's an elevated solitary wave or a depressive solitary wave. If sigma is greater than a third, you get depressive solitary waves. We can find the energy in non-dimensional terms. The energy is written like this. Integral of eta u is dq dx and this is eta, and q dx, so just u. So you find all the terms of eta to 9 orders. You find q to 9 orders, you take its derivative, you put it in the symmetry. This interval contains kinetic energy, potential, surface energy. The kinetic energy, you have to use Green's theorem to come back. I'll also talk more about that in Beijing, how you do all these intermediate calculations. But here's the result. For sigma less than a third, the energy versus the non-dimensional amplitude, the maximum amplitude. Okay? When you are here, you're at the maximally energetic wave. Long and Higgins found this. I don't think he plotted it right this way, but he found this. There is a maximally energetic wave. The Stokes wave, which has a 120-degree angle, is actually over here. It's on the, not the maximally energetic wave, interesting. There's a lot of reasons to believe the maximally energetic wave is the stable wave. When sigma starts increasing, you have this structure, but the energy starts decreasing. Sigma 0.1, sigma 0.3, energy is practically so this is a plot for sigma less than a third of the maximally energetic wave, the maximum amplitude of the maximum, the amplitude of the maximally energetic wave as a function of sigma. And sigma 0 agrees with Fenton and Long and Higgins. I haven't seen it done outside that regime. Here's for sigma greater than a third. Here's and this is depressive waves, so they go down. And they were first observed in 2002, depressive waves. So one would suggest that these are the biggest waves you might see. Sigma's 1. This one, when sigma is very large, the maximum occurs right at the edge, near a non-dimensional depth of 1. Here's what the maximally energetic wave goes to. So when sigma is very large, this suggests, at least in the inviscid limit, that the wave is going to go right down to the bottom and still be stable. Here are some wave profiles. Epsilon is 0.1. When sigma is 2/3. So I'm now just talking about this one. Epsilon is 0.1 is over here. Very nice profile. Then you look at the profiles as you increase epsilon. And they're very nice until the max. Just beyond the max, they start getting crinkly. Suggesting they're not stable. Whether they are or not requires us to do more analysis, and that's another topic.
Does the inflection point in the profile at epsilon equals 0.268, does that correspond exactly to the peak of the amplitude?
Yeah. Suggestive. Very suggestive. And then we did it for 2D. Now these are lumps moving along. You do the same analysis, and the leading order problem is Kp in the steady frame, because we're talking about lumps. And we can solve this. We know what Q0 is. Okay? Because it's a rational function. I wrote it down earlier. Essentially. I wrote down eta, but Q and eta are related through derivative. So we know Q0. The only problem is that we cannot find analytically the higher Q1's eta ones. We can't do it. Maybe you can. So we had to do it numerically. Nevertheless, we were able to do it, and we were able to go 2 orders, because the numerics gets a little ahead. You have analytics, you can go to 9 orders easily. You have to solve it every order. It gets a little bit harder. But at any rate, we can get two orders, maximum depth versus the speed 1 minus c squared, measuring the speed, cx squared plus cy squared. So these are fairly nonlinear features. And here's a wave profile. Typical wave profile. These are depressive waves, so they're inverted from what I showed earlier. And there's your profile. KP equation. Well, I'm not going to be able to go through all of this today. So I'm going to just say this. Come to Beijing, and there I'll show some pictures. Yuji will talk about some pictures, but I have some more pictures to talk about of KP waves in not the lump configuration, but line solitons. This is an area that is of great interest and very interesting, of course, to Yuji and Sharby, because they have these beautiful formulas that describe interaction of line solitons. And I would like to say that you see these, they're prevalent. I looked at the beach very briefly this morning. I think you could probably find them on this beach, although by the time I got out there it was a bit rough. At low tide, you will see interacting waves. This picture comes from my book with Harvey, and you see what I call an X interaction. And this little lip, soliton lip, this interacting lip, the stem of the wave. I call this a long stem. There's short stems, long stems, Y interactions. You see them prevalently. See them essentially every single day on beaches that are flat and long. The one here, I don't know how flat it is, but I think at low tide you probably will see it. Sorry, you have to go to Beijing to see this. Make your reservations. Yuji told me today the Japanese yen is very strong. So no problem. Practically free. Tokyo to Beijing. Well, let me mention a few words about interfacial waves and what we can do there. Well, here's a wave. Density 1, density 2. There's a velocity potential down here, there's a velocity potential down there. There's a velocity potential from the bottom, there's a velocity potential from the top, and there's a. We can find non-local formulation. Two non-local integral equations, eta and little q, that's what we had before, and then for the top one, eta and capital. And then a pressure control. We also can do two free surfaces. You have phi from the bottom